What I'm going to talk about tonight is globular star clusters. But in order to put that in sort of in perspective, we need to sort of look at how stars are associated, or at least how we see them in the night sky. And basically, we have four different types of stellar groupings. We have what we call asterisms, which are chance alignments of stars. We have associations, and these tend to be of young stars. So we have OB associations, which are associations of massive young stars of spectral type O and B. We have what we call T associations, which are nothing to do with down the Women's Institute, but are young stars of the type T Tauri type. And then we also have what we call R associations, and these are groups of stars associated with reflection nebulae. So they're still associated with the material from which they were born. The other defining characteristic of this is they don't tend to be large in number, at least in most cases. So we would have a few tens to maybe 100 at maximum of stars associated with an association. Um, so in the sky at the moment, we'd have something like the Perseus OB association, so a group of massive stars forming some of the brighter stars in Perseus itself. The next collection of what we call open star clusters. And what this means is that they tend to be found in the galactic plane. They're generally young. So the Pleiades, Hyades, for instance, would be examples of these. So, a few tens to hundreds of millions of years old. And you might ask why that is. But the fact is that all the stars go around the galaxy, and because they have a different spread in the direction of the galactic nucleus, they move at different speeds. So over time, the clusters are smeared out. So, for instance, our sun is 4.5 to 5 billion years old or so, and it would have formed in a cluster of other stars, but we don't actually know definitively any of the other stars that were formed with our sun. So over that time period, all of them have been dispersed in space, and we can't find them. Now, occasionally, we do find old star clusters, old galactic star clusters of sort of maybe a couple of billion years old, but there's this very unusual, and their position in the galactic plane usually is their reason why they're still there. And then, of course, we have the globular star clusters. Um, so this is an example of an asterism. This is known as the coat hanger or Brocchi's cluster, but it isn't actually associated stars. It's purely a line of sight effect that just happens to show these stars up in a shape. And there are many of these around. So, for example, the Big Dipper asterism, part of Ursa Major, um, although most of its stars are actually associated, there's something called the Ursa Major moving group. At least two of the stars are purely a projection effect. So in a few million years or so, that asterism will disappear. Open star clusters. So this is an example. This is the H and Chi, a double cluster in the sword handle of Perseus, obviously again up at the moment. And you can see here that the stars are mostly bright blue, which means that they're young, hot stars. There are a few red stars in the field, and these would have been the more massive members of this cluster that have already evolved to become red giants. Now, interestingly, this cluster or pair of clusters may actually be related, so they aren't a line of sight effect. They may be related in the sky. So let's go on with globular star clusters. So um, in general, certainly in the northern hemisphere, most of them are relatively faint, and it was the requirement of, or the discovery of the telescope, which allowed people to start searching the skies for things that they couldn't see, that brought up the first cluster that was known. Um, Edmund Halley spent some time in St. Helena, not looking after Napoleon, but he was searching the southern skies, and he discovered that a star or an object that had been placed as a star, Omega Centauri, was actually a globular cluster, and this could be seen by the naked eye. So he was given the credit for the discovery of that, although, as it says there, um, it was probably well known to southern Aboriginal peoples before that, though probably not as a cluster. There, the resolution wouldn't have been good enough. Now, it turns out that the brightest globular clusters are actually visible to the naked eye, but most of them are in the southern hemisphere. So Omega Centauri, 47 Tucani, M22, etc., are visible for the southern hemisphere or lower latitudes in the northern hemisphere. So um, Omega Centauri you could see from southern Spain, Tenerife, or the Canary Islands. 47 Tuc, you really have to go south of the equator. So this is how they started to be discovered. So obviously naked eye, and then um, William Herschel, who really pioneered um, this, I guess you could say, the study of cosmology, um, was studying the heavens to understand their construction, um, and he found about 2,500 new objects, and they appeared in his telescope to be mostly round, so he coined the name globular cluster. Now, interestingly, although Herschel gave a separate group in his cosmology to planetary nebulae, he didn't give globular clusters their own group. But Herschel found something like 39 new ones, and as it says there, previously 33 were known, and 29 of those were in Messier's catalogue of fuzzy objects. Now, it gives you some idea of the quality of Messier's telescope, or the lack of them, that he was unable to resolve things like M13 into stars. You know, he just saw it as a hazy mass. So it was Herschel really started to work on that. And he discovered most of the brighter clusters that we could see from the northern hemisphere. Now, obviously, he worked from Eton, Windsor, Slough, and when he was doing planets from Bath, so you know UK latitudes. Now, moving into the southern hemisphere, there were fewer people doing astronomy down there, and initially they were more interested in cataloguing stars than fuzzy objects. But a chap called James Dunlop, who was went to Australia as the mechanic with of Sir Thomas Brisbane's observatory, when Brisbane went back to England, Dunlop built himself a 9.5 inch, again, speculum metal mirror telescope. And in 6 months, he discovered something like 600 objects. Now, unfortunately, um, A, his telescope wasn't of great quality, and B, its resolution wasn't that good. So of the 600 objects he discovered, there's probably only 300 would be listed now as a deep sky objects. The others would be unresolved double stars and other bits and pieces. Um, so the person that really went down there to search the whole sky was John Herschel, so the son of William, and he took a similar telescope to William's, an 18.7-inch reflector, down to Cape of Good Hope, and he spent 4 years down there studying the southern sky, and basically finding most of, again, the brighter objects down there. And he discovered amongst that many other globular clusters, though to be fair, Dunlop had found the majority of them, but his positions also were pretty poor. So it's worth noting that, we think we have it hard observing now, but there was one occasion that Herschel was up the 18.7-inch telescope, and there was a pride of lions wandering around underneath the telescope. um, so obviously they weren't interested in climbing because lions can climb quite well. So it probably wasn't the nicest thing at that point. So by this time, there were about 133 globular clusters in the NGC catalogue. So Herschel, John Herschel, put together all of his father's observations and his observations into a catalogue called the General Catalogue. But it became very obvious that people were discovering things at a much faster rate, and the Royal Astronomical Society asked a gentleman called Jean Dwyer to update the general catalogue, and he produced the new general catalogue in Armagh in Ireland. And it's quite amusing because if you read the foreword to it, it sort of apologizes for renumbering everything, and hopes that people will never use his numbers, and continue to use the Herschel ones, which of course almost everybody's forgotten. So there were everything in the NGC was discovered visually, not always by small telescopes. Obviously, Lord Rosse and his crew at Burr with a 72-inch were discovering lots of nebulae as well, but everything was discovered visually. And then 8 more globular clusters were discovered, and they were added to the index catalogue. And the there were 2 versions of the index catalogue, in total about another 5,000 objects, but it was perhaps one of the worst catalogues ever put together, because there was one object in there 5 times. There were objects in there that were already in the NGC. This wasn't Dreyer's fault. He was just given really bad positions, mostly by the Americans. And he was just put them in there. So the IC catalogue was the last general catalogue containing every single object, type of object. And after that, people moved on to having specialist catalogues for each type of object. So despite that, we are still discovering new globular clusters. And a lot of these have been discovered in the near infrared because it penetrates through the dust, and also, as we'll see, from deep surveys, often around the Magellanic Cloud area. So really, what are they? Well, as it says there, globular clusters are very old. So we've said that open clusters can be maybe a couple of billion years, but here we're talking about objects in the 11 to 13 billion year range. So these objects would have formed about the same time as our galaxy. They contain what we call low metallicity. Usually this means very little iron. And this normally comes from old stars because obviously at the beginning of the universe, there was only hydrogen and helium and a touch of other things. So everything else had to be created from other stars. And as it says there, they mostly contain what we call population 2 stars, and we'll go through what those are in a minute. But the other difference between them and open star clusters is that they contain thousands to millions of stars. So, compared to the few thousand you might get in a very large open cluster, these are much bigger objects. As it says there, the size um, varies between 100 to 200 light years across, though there are smaller ones as well. And there may be 200 associated with our galaxy. Now, as it says there, the stars in a globular cluster are very tightly packed. So if you think that our nearest neighbor, Proxima Centauri, is about 4 light years away, the average distance between stars in a globular cluster is only 0.3 light years. And this illustration here is what somebody thinks the night sky as seen from a planet in a globular cluster would look like. So you're not going to do very well on anything in deep space, really, from that, just trying to see between the stars. So I mentioned star populations, and um, a German-American astronomer called Walter Baade came up with this idea in the 1940s. And he came up with the idea that we had what we call population 1 stars, so stars that formed between 1 million to 1 billion years ago, found in the spiral arms, of a galaxy. So our sun, for instance, is a population 1 star. Population 2 stars, he thought, were the older stars found with fewer metals, and in our galaxy, for instance, they would be found mostly in the bulge or in globular clusters. And then we have a theoretical concept of population 3 stars, which formed at the start of the universe. And obviously these are predicted, but it's so far away that even with the James Webb telescope, it's probably unlikely that we'll actually see a population 3 star. The other property of these stars is because there were no hydrogen, there were no metals in them, they could be incredibly massive. So several hundred, maybe up to 1,000 solar masses, which means they lived fast, died young, and spread their process elements into space. So where do we see globular clusters? Well, this is a schematic of our galaxy. We've always, think of the fried egg model. So we have the galactic center. We have the disk or the thin disk where our sun lies and where most of the star forming regions and open star clusters live. We have a thick disk which contains older stars. And then we have a halo around the galaxy. Now, if we're talking in visible light terms, that consists of globular clusters and a few older stars that have been ejected from the galaxy, as well as neutral gas, etc., going around it. Now, globular star clusters can be very loosely tied to our galaxy. So if you think that the distance to the Large Magellanic Cloud is about 180,000 light years, and we think that's fair distance away, NGC, the globular cluster NGC 2419, sometimes known as the intergalactic tramp, is at 30,000 light years, 300,000 light years, sorry, so almost twice as far away. And there's another cluster called the crater cluster, which was discovered relatively recently, that lies at a distance of 470,000, 100,000 light years away. As it says there, it was probably captured from the Small Magellanic Cloud. And it was mentioned that we're finding clusters all the time from deep surveys. So just to give you an idea, this is NGC 2419. It's in Lynx, so it's an object that's coming up at this time of year. It's a very pretty concentration with the two bright stars next to it and the globular star cluster itself. And this is a Hubble view of it. Now, what you need to remember is that Hubble actually has a fairly small field of view. So what we're looking at here is really just the center of the cluster. So it would just be this sort of area in here, and you're not seeing the whole thing. So when you see Hubble pictures of globular star clusters, it really, in general, is just the center. And then here's again one of the deeper clusters out there. But it's not always been easy to determine whether a cluster is a globular cluster or a galactic cluster. The reason for this being that a number of globular clusters, because they orbit our galaxy, can be seen in the plane, and determining whether or not it is actually a star cluster or a globular does take quite a lot of work. So M71 in Sagitta has oscillated between being an old galactic cluster and a globular cluster over the years. It's now definitively thought to be a globular cluster, but it was quite a difficult thing to figure out. And this gives you an idea of the distribution. The slightly little grey dots are globular clusters. And as you can see, there's also little white dots. And the little white dots are dwarf galaxies also surrounding our Milky Way. And as you can see, the distribution is not dissimilar. And then we found a whole bunch of new globular clusters out here. And these were because people were doing deep studies of the Magellanic Clouds and found new globular clusters far out there. So I mentioned that these things orbit the Milky Way, and depending on their orbit, they can either take a very long time, or they can go through fairly frequently, and this has an effect that we'll see later on the globular cluster itself. And this just gives you an idea of the distance. So in the center here, we have our galaxy, and then we've got some globular star clusters almost out at 1 million years, 1 million light years. So almost halfway to the to M31, we're desperately hanging on to some of these things. Now, we can just have a quick look at why we think globular clusters are as they are. So this is the well-known Hertzsprung-Russell diagram, which plots some variation of temperature against some measurement of luminosity. And it turns out that most stars, when they're burning hydrogen to helium in their cores, fall on what we call the main sequence. So if you really want to know, a star will start forming over here. It'll sort of migrate onto the main sequence. It'll spend most of its life on the main sequence, but then at some point, the hydrogen in the center runs out. The star will start to expand and become a giant. Depending on its mass, it may start turning hydrogen into, or helium into carbon in the center, and blow up even more in size, that is. But you can see here that the more massive a star is, the shorter its lifetime is. So one of the things that astronomers look for when they're trying to age a cluster is what we call the main sequence turn-off point here. So this is when the stars are leaving the main sequence and becoming giants. And that gives you an approximate age for a cluster. This, of course, is just a descriptive one, but this is a real HR diagram for a globular cluster. And you can see here that this is the turn-off point, and stars are migrating up the red line branch, And eventually they will start to cool off, pass through here, and come down and become white dwarfs. Um, we'll discuss what these are later on. So as you saw for that distribution, there does appear to be an overlap in the area where we find dwarf galaxies and globular clusters, both in terms of location and in terms of size. So what's the difference? Well, it appears that dwarf galaxies appear to contain dark matter, whereas globular clusters don't. And we're talking about the invisible form of dark matter. And some dwarf galaxies actually have far fewer stars than some of the globular clusters. Um, but recently they found some globular clusters around the galaxy NGC 5128 that may contain known types of dark matter, i.e. black holes. As it says there, none have been found in our galaxy so far. Now, this is perhaps unexpected in the sense that globular clusters are very densely packed at the center, um, but they don't. What we were looking for was not stellar mass black holes, but sort of black holes in the 1,000 solar mass category, the intermediate size ones, which we don't seem to have found anywhere really. There seems to be a huge gap between stellar mass and sort of supermassive ones at the center of galaxies. Now, it may be that they contain very tight binary stars which bind the energy there. And many globular clusters contain lots of millisecond pulsars. Now that itself is interesting because pulsars form when from the explosion of a massive star, the nucleus then either becomes a neutron star or a black hole. So you would, and when they're born, they spin very fast, but you wouldn't. They tend to slow down with age. So you wouldn't expect to see fast spinning pulsars in an old object like a globular cluster. Now, it turns out that what we think is happening here is that these pulsars have become joined in a binary system with another star, and they are actually sucking matter off that star and spinning up as they do so. They're also known as black widow pulsars because they tend to eat the star they're going around. So that has been was a surprise when first found, but that's the way we think it works. Now I mentioned black holes in things, and about a year or so ago, this was put out. This is an X-ray um, observation of a globular cluster, and they found this X-ray source right in the center. And there was excitement thinking, oh, we've finally found the black holes we're looking for. Unfortunately, and they put that out, unfortunately, later observations showed that that almost certainly wasn't the case. Now, we also find some strange objects in globular clusters. As I said, most globular cluster stars are less massive than the sun. They are reddish in color, but globular clusters contain blue stars, which, as it says there, shouldn't be there given their mass and age. So again, we've had to look at how these could have formed. And as it says there, there's two possibilities. One is that they come from two normal stars in a binary system, and mass transfer between them has given one of them more mass and it's sort of heated up to look different. And also possibly that they could have come from stellar mergers. So, stars are unlike in our galaxy, which they're far apart. These are so close together that they could have actually merged. So we saw that on this diagram. So we've got the main sequence here, and then we see the blue stragglers out there, and they really are blue. So this is again, a Hubble image of the center of a cluster, and you can see these blue stars in it. So, as I said, it really is, they really are blue. And then some clusters like M5 actually have a huge number of these, which makes it more difficult to understand. Now, apart from stars, as it says here, there's not much, if any, gas and dust in globular clusters. Now, that is slightly surprising. You'd think that, these are old stars, they are throwing out material, um, so dust and things. So the most likely scenario there is that on every orbit, a globular cluster will pass twice through the Milky Way plane. And although the stars in general aren't impacted by the matter there, the gas and dust is. So there's an interstellar medium, as we know, and the ram pressure of that may be stripping out all the gas and dust from the globular cluster as they come through. Um, there are also we only know of 4 planetary nebulae in globular clusters, and it says there we might expect 16. But in fact, I believe that we're down to 3 now because the one around NGC 6441 is now not believed to be associated with the cluster. But these are the ones that are there, P's 1 in M15. This is doable with 40 centimeter telescope, well, not 40, maybe 45 centimeter telescope. You need a very good chart and obviously an O3 filter. This one in M22, there are claims from Americans to see it. I do have my doubts about that. And I don't believe anybody has visually seen those two. I mean, obviously in America they do have larger telescopes to work with. So globular clusters, this is M15. It's very centrally condensed, and here's the globular cluster. Sorry, the planetary nebula. And then again, if you've got Hubble, you can shoot that. Again, note that this is actually relatively close in. So although it looks a long way out, the Hubble field of view is quite small. And now the other thing that we find with globular clusters, they appear to be related to the size of the galaxy. So the Andromeda Galaxy M31 may have 300 globular clusters. The Sombrero Galaxy M104 may have 13,000 of them, and M87, the giant elliptical at the center of the Virgo cluster, may have 15,000. As it says there, this may be associated with the number of mergers a galaxy has undergone. And when you get into big clusters of galaxies, then you can end up with globular clusters just wandering lonely as a cloud through the galaxy itself. This image is probably the largest image that Hubble ever took in terms of the number of different fields they had to take, and it was to study the center of the Coma cluster and look for free floating globular clusters. Now, it's difficult to tell from there, but this image, every little green circle here is believed to be a globular cluster. So you can see, they are associated with galaxies, but there's obviously wandering ones as well. So they would have been, torn out off the galaxy they belong to in interactions in the cluster. So we next get on to formation of them. Now, as it says there, the process of forming globular clusters isn't well understood. And that's partly because they're very old, so they formed a long way back in the universe, and it was difficult to see what's going on there. And obviously, with James Webb, we hope to see some more. As it says there, they may come from massive young clusters formed in galaxy collisions, i.e. the antenna, or they may have come from massive starburst clusters like Vesterland 1 in our own galaxy. And as it says there, it's not even clear it's a single event. Now, if you spoke to people 20 years ago, they would have said that globular star clusters have a single generation of stars, and they all form together. Now, that's not necessarily the case anymore. More detailed observations suggest there may be one or two generations of stars in a globular cluster, and sometimes more. And as it says there, most of the globular clusters associated with the Milky Way form with it, or potentially even before it. So this is the antenna. It's in Corvus. It's two interacting spiral galaxies. So we've got one here and the remnants of one there. But you can see there's giant blue clusters of stars forming in this collision. And obviously in the early universe, galaxies were colliding very often, and possibly that's where they came from. And then this is Vesterland 1. In our galaxy, it's got a huge number of very massive O and Wolf-Rayet stars, but also associated with it, there'll be lots of low mass stars as well. So this is another possibility for forming these things. And we've sort of already covered that. Now, the other possibility is that not all globular clusters form the same way. And we now believe that some, Omega Centauri in particular, and also M54, may actually be the central bulges of dwarf galaxies formed that have been swallowed by the Milky Way. Now, one of the reasons we think this with Omega Cen is that in most globular clusters, stars are going around the center at sort of random angles, but there's no general rotation of the cluster itself. Now, in the case of Omega Centauri, there is a general rotation of the cluster. As you can see from the image there on the left, it does appear slightly flattened or egg-shaped. It also happens that there are probably about 4 different generations of stars in that, which again would suggest maybe a slightly different way of forming. Now, our galaxy is busy devouring a small galaxy called SAG-DEG, Sagittarius Dwarf Elliptical, and we have reason to believe that what we think of as the globular cluster M54 is actually the central bulge, or what's left of it, of that galaxy. So this is just another larger scale picture of Omega Cen, and you can see that it is distinctly flattened compared to the others. So where did globular clusters fit in? Well, in 1918, Shapley used just the distances to globular clusters to show that the sun was not at the center of the galaxy, and the galaxy was much larger than anyone had thought. So this was, we'd moved away from Earth, center of the universe, sun, center of the universe, galaxy, center of the universe, as things were going on. And he came up with an idea that the galaxy was maybe 300,000 light years across. And, this is much larger, obviously, than what we think it is now, which is about half that. And to do this, Shapley used short period variable stars in globular clusters, known as RLRA, and he realized that, like the Cepheids, their brightness and period was correlated. So the longer the period, the brighter the star was. However, he didn't have a 0 point for the relationship, by which we mean he couldn't there was no RLRA stuff close enough to us to measure distance to it by another method. So, he was having to statistically guess what the 0 point was going to be. He didn't know about interstellar extinction, which means that A lot of the globular clusters that were near or close to the galactic plane were seriously reddened. Um, and so his calculated distances were too large. Um, but the general hypothesis was correct that the galactic center was in the distance, um, and the globular clusters went round it. And as it says there, we now know that RI Lyrae stars are low mass Pot2 stars. And this just gives you an idea of the different period luminosity relation. And this is obviously what we use now to try and get distances to galaxies. So the RI Lyrae stars were down here. But it wasn't just Shapley that was confused by this. So when Edwin Hubble started measuring the periods of Cepheids in M31 and M33, um, he didn't realize that in fact the stars he was looking at were actually type 2 Cepheids, known as W Virginis stars, rather than type 1. So his distance to M31 was under, well, half of what we think it is today. He came up with about 800,000 light years compared to the 2.2 that we know it is today. And just as an aside, in case you think this isn't going on, it's actually next month, January 2025, that's the 100th anniversary of Hubble showing the distance to nebulae. The paper was published in 1925, January. So hopefully there'll be some celebrations of that. So this again just shows the distance and the distribution of clusters close in. And this illustrates Shapley's problem. So here we have the globular cluster M4, and here we have M81. And as you can see, the M81 obviously is further away, but also it's hidden behind sheens of dust, which are going to impact on any distance measurements to it, unless you can get an extinction. So here again, we have M4 and M81. But the other thing that Shapley did, along with his student Helen Sawyer, was to try and categorize globular clusters. So again, in the early part of the last century, we didn't know a lot about them. And one of the easiest things to do was to try and bin them into some form that we could then look at. And they came up with a concentration class system. And this was the original paper. It didn't reproduce terribly well. Now they did a lot of work on that, and this was also all done visually, looking at photographic plates, as it said, and the Franklin Adams plates. So they're very useful to the visual observer because class 1 is going to be tightly concentrated, easy to see, whereas class 12 is going to be faint and dispersed. Unfortunately, professionals dropped the idea of classes, so well, it wasn't much use to them, so most new clusters don't have a class assigned. But to give you an idea, this is in coma, so this is M53, rather nice and easy to see globular cluster. And over here is, I think it's 5466, which is a class 11 cluster. And as you can see, it's much fainter, much more diffuse. And it's actually quite difficult to see. And certainly if the conditions are hazy, finding it is quite challenging. So this is M15 again. This just gives you an idea of some of the different kinds of clusters and how they were concentrated together. So there is a variant of these things. There's Omega Centauri again. Now, this is a relatively recent discovery, so about 1970s, I think. This is Terzan 12, a globular cluster deep in the Milky Way. And you can see here the problem. So this is part of the cluster. But this is an obscuring cloud of gas and dust, and you can see that the cluster is hardly visible at all there. So this is why we've had, difficulties finding more of them. Now, they don't last forever. So as it says there, as the cluster plunges through the plane of the Milky Way, then the gravity of the Milky Way strips stars on the outside from it. And as it says, the cluster is small or on a short orbit, then eventually it'll be destroyed, and its stars will join the general halo and maybe leave a faint star stream. Now, the Gaia satellite has over the years has shown that there are a number of star streams, associated stars, that may have come from dissolved clusters. Again, just as an aside, next month Gaia will be turned off as it's run out of propellant. So, I mean, it'll be years before they get the final catalogues out of it, but it's done incredibly well for the time. And just to show, this is an example. This is the globular cluster Palomar 5. This is its center here. And this is the stream of stars that have been pulled out of it as it goes round the galaxy. So over time, it's going to evaporate. As I said, we're currently merging with SAGDEG, and part of that merger, we're possibly gaining 6 new globular clusters. So, as I said, we think M54 is the core, and then these others are globular clusters that originally would have been it, and now are ours. Now, it turns out that we've had a number of merger events over the 13 billion years or so, and we seem to have gained quite a lot of them, of globular clusters from this. So it says that they do tend to give them entertaining names. So the koala or kraken merger was one of the earliest ones, and we gained this lot from it. The Sequoia merger about 10 billion years ago. This is where we think we got Omega Cen from. The biggest merger, I think, in our galaxy's history was this Gaia Enceladus merger. Um, and that happened 9 to 10, 11 billion years. And we've got things like M13 as part of that. So we have collected quite a few globular clusters of the ones we've got from these mergers. And then this was one of the most recent um, attempted mergers. You can see it's not so easy. So M13 is included there. It's also included here. Um, so, you have to take sometimes a pinch of salt. So after the NGCIC, the next sort of big group of globulars that were discovered were from the Palomar Sky Survey in the 1950s. And they found something like 15, well, not something like, they found 15 globular clusters as part of that survey. However, they weren't terribly good at checking. So Palomar 7 had already been discovered. It was IC 1276, I think, and Palomar 9 is a NGC one, but all the others were new. As you can see, some of them are, well, quite difficult to distinguish from the background. This is Palomar 2. After that, the next sort of burst was from a Frenchman called Terzan, who was working in the near infrared, and he found, well, it says 12 clusters, but in fact, I think he may have discovered one twice, so there's actually only 11 real objects there. And as it says, most large galaxies appear to have their own globular cluster systems, mostly acquired by mergers with other galaxies. So if you want to visually look at other globular clusters, then obviously there are a number in the Magellanic Clouds. The Fornax dwarf galaxy is actually quite tricky to see visually, but some of its globular clusters are much easier to see than the galaxy itself. So here's a sombrero. Just recently, there was a James Webb image of this published, and it's originally it was thought to be a large spiral. It's now unclear whether it's a large elliptical that's just merged with a spiral, but it's almost certainly not a spiral by default. But many of these faint dots around it are actually globular clusters. And this is M87, and you can see again, look, where's it gone? Many of the little dots here are actually globular clusters rather than stars. It's just a more detailed view. So we'll sort of just finish off with how do we observe them? Well, as it says there, unlike galaxies, which they can take high magnification, at least in the brighter and more compact cases. There's targets for both small and large telescopes and obviously binoculars. And in case you think they're all the same, then when you're looking at them, look for shapes, concentration, star patterns. So there's the well-known propeller asterism in M13. And if you're really wanting to go for it, you can look for the Planetary Nebula in M15. So as I said, there are many bright ones. There are 29 in Messier's catalogue, 133 in the NGC. As I said, these will all have been discovered visually, though not necessarily with small telescopes, and 8 in the IC. And then we've got the specialist lists such as Palomar and Terzan. M13, brightest globular cluster in our sky. It is visible to the naked eye from a dark site, so I would have thought that Herefordshire would be a good place for that. And you can see it. Well, I don't know if you can see, but this is the propeller asterism that you can see, and you can see that visually. Actually, it's easier to see visually than it is to see on that picture. We all know where it is. It's up in the keystone of Hercules. Hercules actually has 3 globular clusters. There's M92, which is a very nice bright globular cluster, and another one that's much fainter. Now, when in 1974 they beamed a message about life on Earth towards M13. Now, I don't know if this was actually towards where M13 is now, or where M13 will be when it message gets there. So who knows whether it'll get there. It says there most globular clusters in the center of our galaxy, so the best time to see them is late spring and summer. It also, as it says there, means that many of them are low in the sky. And in the case of Ophiuchus, which has 25 globular clusters, there are very few bright stars to go for. Only Sagittarius, which has 31 globular clusters, has more than Ophiuchus. There are around now, so M2 in Aquarius, M15 in Pegasus, M30 in Capricornus, and then there's a few in the winter, M79 in Lepus, often tricky because it's below Orion, a long way below Orion, and can be quite faint and disappear into any kind of trees that are around, and then Palomar 2 in Auriga. So where do you find information? Well, these are a couple of Webb links which have lists of globular clusters. So Harold Corwin put together a list, and the British Astronomical Association Deep Sky section has a observing program on globular clusters. Whether anybody's actually observing, I don't know. The BAA Deep Sky section doesn't have a very good record of people following its programs. There are a number of observing lists. So the US Astronomical League, which is their equivalent to the FAS, but actually does something, has a globular cluster program. And then there's various kinds of software that can be used to create, as it says there, customized lists for your location and equipment. And the three that are currently still being developed are Sky Tools 4, Deep Sky Planner 9, and Astro Planner 2.4. This just gives an indication of globular clusters from Sky Tools. So I've taken the AL's globular cluster list. I've given it my 15-inch, and I've given it a date, and it's come up with this number of globular clusters it thinks I should be able to see. The red says it's going to be bad, which, as you can see, it's full moon. It's not surprising. Um, this is Deep Sky Planner. Again, this has created a list of the Fornax globular clusters. So if you'd gone to Tenerife or something, this would have been useful to see. And then there are a number of other resources out there. So there are, as I said, globular clusters visible in M31. So G1, which is or known, or Male 2 as it's sometimes known, is its equivalent of Omega Centauri. It has been seen in an 8-inch, but it's going to be tricky. It's much further away from M31 than you might think. There are some globular clusters visible in M33 if you have larger telescopes, and then we've already discussed the LMC, SMC, and the Fornax dwarf. So this is Andromeda. This is just showing the locations of some of the globular clusters. And there is a program called Megastar 5, which is free now, which has a list of almost all of them. And as you can see there, you can plot up huge numbers of globular clusters if you so wish. For those people that use the Nexus DSC, we've put together a catalogue of the globular clusters in M31 and M33, should you wish to try and use that to find them. There are a few books. So the Webb Society Handbook, obviously somewhat out of date now. Volume 4 would have been published in about 1978 or so. But for people using smaller telescopes, it still provides a reasonable list and descriptions of what's out there. The definitive guide is probably this one, Star Clusters, published by Wilman Bell, though it's now difficult to get hold of. And then these two books. This one is describing the evolution and astrophysics sort of star clusters. It's not an observing guide. And then Mike Inglis has produced an observer's guide to star clusters. The AL has a guide to its globular cluster observing program. Unfortunately, this costs money, and because of postage costs, shipping it from the US to here is expensive. And then Alvin Huey put together a downloadable guide of the globular star clusters, or we do actually print it out and sell it on the web from the Webb thing form. So that covers all known globular clusters. So that's what we've got. This is index of the web pages from the Adventures in, pardon me, just a minute, that's not. From the Adventures in Deep Space, and they have quite a lot on looking at both normal suns and extreme ones. So there we go. Thank you very much. And if you have any questions, I shall try to answer them.
Well, needless to say, Owen, that was magnificent, wonderful, thank you. I think I said to you last time that planetary nebulae make a great topic from a visual point of view. If you were talking about black holes, you'd be relying a lot on mathematics and graphics, but because almost by definition, you can't photograph them. And I think globular clusters of every shape and hue also are great material for very beautiful. They make beautiful objects, don't they? They really do. Some of them are quite mesmerizing. That kind of, they almost make you feel as though the larger ones and those very detailed pictures. make you feel as though you're being almost sucked into some kind of Stargate or something. I don't want to get all Star Trekky or 2001-ish, but they are quite mesmerizing objects. Thank you ever so much. So let's begin, as we always do, ladies and gentlemen, with a resounding, either virtual or physical to the camera, round of applause. Thank you very much indeed.
Thank you.
It's not quite the same online, I'm afraid, Owen, but I'm sure you appreciate the sentiment anyway.
No, I do. Yes.
Yeah, I'll just kick off as usual with just a couple of comments and question, and then I'll hand it to the floor. Um, I mean, I really did not know, and I knew that you would enlighten me on in so many aspects of clusters. I really didn't realize there was so much complexity to their shape, their form, their size, and in particular their genesis. But I was aware of, certainly in the case of the Milky Way, this kind of diaphanous cloud, this halo about which our own local, shall we call them local clusters, revolve. Um, if I've understood you correctly, they basically orbit the galaxy through this halo at more, I wouldn't say perpendicularly, but certainly at acute angles to the plane, the galactic plane. And that's not necessarily a definition of them, but their motion is generally at variance with the general movement of the arms and the plane. Is that correct?
Yes, I mean they have really no relation to the way that
No.
the galaxy is spinning.
Yes.
And some of them, as we saw, are a long way out. And the halo clusters tend to be, all the deep halo clusters tend to be the more massive ones because they haven't
Yeah.
passed through the Milky Way. Now, if you want to add complexity in there, of course, we tend to think of most of the halo being dark matter, but that doesn't tend that just impacts the gravitation of the galaxy. It doesn't seem to make much difference to the globular cluster orbits.
Yeah. I mean, the reason I'm homing in on that is because it seems to me, I mean, if if a cluster is, I think you mentioned this process whereby they get smeared and they get stretched and eventually dissolved, I think was the word you
Mm.
used. If they get trapped or pass through the plane often enough, they effectively become part of that plane and they become smeared out and they're more sort of, you know, generally that they lose their concentration. Um, and you also mentioned that the larger the galaxies, the more clusters we seem to
Mm.
see by and large. Is that correct as well? I think you said.
Yes, so large galaxies tend to be born by accreting other galaxies. So
Yes.
a bit like, we're getting six globular clusters from the
Yeah.
Sagtag merger.
So they're being
Um,
borrowed or acquired. Yeah.
yeah, and it seems that for very large galaxies, they've grown from um, accreting many other galaxies, and that's where the majority of their globular cluster system has probably come from.
Yeah, but what I'm driving at, I mean, accreting globular clusters, borrowing them or acquiring them from other galaxies, still means that they retain their, by definition, they've still retained their integrity, and they're just suddenly they're guests of an even bigger host, as it were. But what I'm really driving at is that, if you think of galaxy formations, on an even bigger macrocosmic scale, you have this heterogeneity of matter, of density, of gravitational fields as the cosmos grows. And you get this clump, this lumpiness, this famous lumpiness that we observed. And that produces islands of stars, which eventually the massive one become we call galaxies. Is it not really just part of the process of galaxy formation that these clusters have simply had enough concentration to have a gravitational field of their own, in that they have a shape and an integrity? They are still gravitationally bound by the host, but they are slowly but surely becoming part of the they're just the last remnants of that, on a much bigger scale, that galactic formation, which hasn't yet smoothed out to be completely homogeneous. You see what I'm driving at?
Yes, but I think you're perhaps misunderstanding galaxy formation. So
Uh-huh.
um,
Quite
we
possibly.
believe that galaxies, or the matter that forms galaxies, were accreted in density fluctuations in the dark matter. So the matter flowed in there and started to form, whereas globular clusters don't appear to have any dark matter associated with them. So this is, as I said, one of the challenges to try and understand that their method of formation was different from the way that galaxies formed. Um, and
Okay.
as you're right to say that yeah, we've acquired them, but over the 11 billion years that the say from the galaxies from the Gaia Enceladus merger, these things, some of them will have been torn apart. Their stars will be just generally in the halo. And as I said, that was one of the things that Gaia really showed us was that these star streams were the remnants of galaxies had been merged, or possibly even globular clusters, and we could see stars moving together and globular clusters associated with those streams. And that's how we came to understand how the globular clusters came with us.
Okay.
So it's nothing
That's,
to do with the homogeneity, that they form differently from galaxies,
I
and
see.
we'd like to know why.
Sure. So that makes them more curious as objects. It's not simply a matter of just areas of mass which haven't yet been absorbed into the greater galaxy.
We don't
It's
think
something,
so.
no, it's something more complicated.
Mm.
Thank you. Okay, I'm going to hand it over to the floor. Would somebody like to ask Owen a question?
Yeah, I've got one. I don't know how far back, distance-wise, you can still observe. Obviously, this is with big scopes, Webbs and etc. You can actually observe globular clusters, but assuming you can go back a fair distance across the universe, can you get an idea of looking at how the chemical change in their like metal? I can never say that word. The metal content. Has had an impact on how their evolution might understand the difference between that and, as you just said, the galaxy formation.
Yes, so obviously one of the problems with the further out you go, the smaller a globular cluster gets, and it's very difficult to do a chemical analysis on its stars. But that's how we age the globular cluster systems that we've got. We can look at its metallicity, we can look at get an idea of how massive the stars are, and that'll give you some idea of how they've been evolving since their birth, and we can see that with the Magellanic Clouds, and particularly the Small Magellanic Cloud, which hasn't had a lot of chemical evolution, and the globular clusters associated with that tend to have very low metallicity ratios. So they have been, evolving with time. The LMC ones are somewhat more metal rich because the LMC obviously has been making stars at furious rates, etc. And that's again how we have discovered that there are multi generations of stars in some clusters because they have different chemical properties and therefore must have formed at different times.
Okay, cool.
Somebody else?
Following up probably from Chris's question, so are you saying that the clusters are formed independently of galaxies, and the only reason they're in galaxies are because they absorbed by one galaxy and then another galaxy absorbs them? Or is it a bit of a mix that some are independent and some were formed within galaxies?
So the Milky Way does have its own globular clusters that were formed with it. Um, and the others, as I say, were associated with another galaxy that's been merged with the Milky Way itself. So in general, globular clusters do form around galaxies, and that they'll stick with them until they another event that causes something to change. So um, so that seems to be. I mean, the problem at one point there was a problem that the ages of stars in globular clusters was older than the age of the universe, which is obviously a bit of a challenge. I think they've managed to sort out their star models to make them up. But they are, as you said, they're of the order of 12 billion years old, so they are very close to the age of the universe.
Somebody else, or I've got just a couple of comments on nomenclature, actually, just on the not so much about what you were saying, but just you mentioned the is it the Shapley-Sawyer concentration system, which I think you said is now being dropped, really, with 12 categories of concentration from nil to very tightly packed nucleus. It just seems to me that it was just overly complex. I don't know why they needed 12. I mean, when we talk about galaxy shapes and barred and spiral, even that doesn't go that deeply. It just seemed to me an awful lot, really. I thought perhaps you could have got away with about 6 classifications. Do you not agree?
Well,
Just
I
seems
guess they felt,
overly elaborate.
well, I guess they felt that the way that the globular clusters were showing different sort of concentrations, but they needed a more complicated system.
Yeah, I
I would
suppose
agree
so.
with you that once you get beyond class 10, so 11 and 12, it's very difficult to
Very
see
arbitrary. Yeah,
any real difference
yeah,
in them. But as I said at the time, you have to remember that they didn't know what they were looking at really, and they were just trying to
sure.
understand things.
Mm,
And it may also have come from the fact that, I mean, I've never seen the Franklin Adams plates, um, but it may just have been that the plates weren't giving um, a great form to what they were looking at. So, I mean, as I said, it's all done visually. They were, looking at the plates. But from our point of view, as amateurs, it's quite useful to know what the concentration class is. And then
mhm,
you've got an idea of how difficult or easy it's likely to be.
mhm. And the other thing was just about the populations 1, 2, and 3. Who remind us again, what was the name of the person that came up with that
That was Walter Baade.
Barder? Oh, Barder, as in
Yeah.
the
So
star
he was
classification.
a German astronomer that left during the pogroms in the 1930s.
Yes.
But of course, he was still regarded as an enemy alien in the States.
Uh-huh.
Um, but he was allowed to use the Hooker telescope during the blackouts in Los Angeles, so he had sort of great skies to work with. Yeah, he came up with the idea of different types of stars based on their metallicity, really.
Yeah. Is that the same Barder that came up with the Greek lettering for the stars? Surely not. That was somebody else. Another Barder, is that? Or
Came up with what?
the basic magnitude classification by using the Greek alphabet in constellations. Wasn't that the
No,
Barder?
that was
Different.
Watson and people. No,
Yeah.
Barda was
There was another Barder who was
yeah.
involved. Yeah. No, the question was, just seems curious, why are the oldest stars population 3 and the youngest population 1? You would have thought it would be the other way around,
You'd have to ask him that.
but fair enough. It just seems like it would have been the other way around. It's a bit confusing, but there we are.
Chris, are you thinking of Bayer Flamsteed?
Oh, Bayer. I'm thinking Bayer, aren't I? Thank
Yeah.
you, Neil. Not
Yeah.
Barder, Bayer. Yeah.
Mm.
Yes, Bayer. My apologies. No connection whatsoever. Right. Anybody else? Or are we done? Anybody?
Are there any thoughts as to whether, in theory, some of these stars in the clusters would have planets? Is there any reason why they shouldn't?
Well, I would have thought that because the stars are packed so closely together that planets would have been disturbed away from that. So there may be free floating planets, but I would be surprised if well, I guess we're surprised that so many stars have planets anyway. So there must be the possibility that they do have planets going around some of them.
Somebody did a study on exactly that either this year or last year, and found that there were more interferences in planetary systems than than have previously been thought, which is exactly what Owen just suggested.
Mhm. You can imagine what the sky would look like if you had a planet and you were viewing from that planet.
Yeah, unfortunately, they're a bit too, even the closest ones are a bit too far away to use any of the techniques that they're using at
Yes,
the moment.
yes, I can well imagine. Yes.
Yeah. Yes, it's tempting, isn't it, to imagine what the view would be like from a planet on a star in the nucleus of a cluster, or for that matter, in the nucleus of a large galaxy, a dense galaxy, or an elliptical, or something like that. But we can't ever know, really, can we? But we can only have the famous artist's impressions.
Well, I think the
Okay.
best would be to be on the outside of it, so you could see the cluster and then see the rest of space as well.
Yes,
Yes,
yes.
that would be yes, the same if we were further out in our own galaxy, we'd probably have a better view. We're just too close, we're too much in it, aren't we? Even though we're not in the center, but yeah, vast distances, quite unimaginable. Okay, I think we're done. Is everybody done? Well, Owen, once again, it only remains for me to thank you from the bottom of our hearts once again. It was a wonderful talk, and I'm going to give you a virtual reaction as well as so thank you very much indeed.
Thank you.
Just on a personal note, are you British born but you grew up in Toronto, or actually Canadian by birth?
I'm
Mentioned
Canadian by
Toronto
birth,
in your
so we lived there until about 1967 or so.
okay.
So then it came to England. So I went through most of my education in their system, and when I graduated, I went back to Calgary, and was working there for about 4 or 5 years in the oil and gas business, and then
Yeah.
I was laid off in one of the reef purges and came back to the UK and immediately got more jobs. So I thought, well,
Yeah. Okay, just curious. Well, thank you ever so much. That was wonderful. We don't have an observing night in December, even if the weather permitted, because it's too close to Christmas and the moon doesn't permit the right sort of social time, if you see what I mean. So we convene again for our AGM, which you probably would have seen before on the rolling schedule on the 9th of January. Do make a note, everybody. It's the 9th of January, which is the second Thursday of the month, simply to avoid the festivities and, as James said, the hangovers of possibly the 2nd of January. So it only remains for me to wish you all good night. And I know it sounds very premature, and to you especially, Owen, a very happy and peaceful Christmas and a lovely New Year. And Owen, I know I've looked at your catalogue of talks. There's still more to come. I'm sure I will grab you again, and
okay.
maybe we'll have a better turnout next time. But I think Christmas is starting to bite. So yes, on that note, Merry Christmas, everybody. Thank you very
No,
much for
you.
attending.
Thank
I'm
you.
going to just close off the recording. I hope that stopped. Yes.